Good morning, everyone. Hopefully the nicer weather we've been experiencing has been good for everyone. I know I've enjoyed it. The cooler weather is more invigorating in the mornings. Um, Hopefully, uh, the remainder of the hurricane season will be diminished for us. I think that would be something that we could all appreciate. But I'll keep my fingers crossed. Now, what we want to do today is I want to do one more example with the indeterminate form. Again, indeterminate form is useful because of the theorem with L'Hopital's rule, which allows us to apply the calculus of derivatives to compute limits. And so it's a very important tool and a very useful tool that you're going to find many uses for as you continue in mathematics, in physics, and certainly in engineering. So maybe we don't introduce it as soon just to make sure that you understand the concept of limit and the rigor involved in that. But now that you are in Cal 2, you can utilize the result to whatever need you desire. So the good thing about Calculus 2 is you have so many new techniques open to you that you can utilize to make your work more efficient. Now, for the last problem in the homework, again, your homework is randomized. There is a problem uh, which is actually a L'Hopital rule from the L'Hopital textbook from 1696. So I guess we don't have to worry about copyright with that. So um, what I have here, let me adjust this a little bit, is a problem from the 1696 calculus text. And this is true. This is in your WebAssign, 1696. So uh, individuals have been doing calculus for a long time, and I think they were just as perplexed then as they are now. It certainly is what it is, and I don't know that it's necessarily any easier. We do have the computer and computer algebra systems, but still the same level of rigor that we use is what was used back in the early days. Um, However, now we have education is more widely available to the population. And so more people actually learn the calculus than did during the days when this was introduced. So L'Hopital's problem, you can see what he has here. He sets A to be a positive number, and you've got all these radicals here, which make the problem somewhat unfriendly. So we're going to convert those. But the original problem was the square root of 2a cubed x minus x to the fourth. That's the radicand. Minus a, and then using the more archaic notation, which is still valid, a times the cube root of a squared times x divided by a minus the fourth root of a times x cubed. So what I wanted to do first is just clean up f of x and make it more user friendly to do computations. Lots of times we think, well, we'll just stick with the way it is, but that's no good. We like to be able to take derivatives using the power rule, and so if that's the case, let's make it more user friendly. So let's go ahead and operate on this a little bit. So we're going to rewrite f 2a cubed x. Really, that's what we've been doing in this class, just taking what we already know and making a few modifications to introduce new techniques. Lots of trig, right? Do a lot of trigonometry. And then we have minus a, and then we have a squared x to the 1/3. Okay? And then our division line, and then we have a minus, again, a x cubed to the 1/4. So let's just keep going. Let's use our laws of exponents to make it even more clean because you know a is a constant. So the first one is fine. We get 2a cubed x minus x to the fourth 1/2. So if you're tutoring someone, this would be a good example to practice the laws of exponents. So we get minus a times a to the 2/3 times x to the 1/3. And then downstairs, we're going to get a minus a to the 1/4, and then times x to the 3/4. Now what we can do is combine like powers, and then I think we'll have a form that will be easy to use. So again, the first part is fixed. So we have 2a cubed x. Again, the court reporting is just as important as the computation. So here, of course, the a, that's a 1. So we'll think of the 1 as 3/3. So this will give us a to the 5/3. And then, of course, x to the 1/3. And then downstairs, looks like we're ready to go. So now when you think about doing this particular problem, we can operate on this. Again, you don't have to do the preliminary work, but often, you know, it's like when you're learning trigonometry and you're learning about reference numbers and things, and you do all the sidebar, then you apply it to the problem, or you work it through linearly. I mean, it really just depends on how much work you have to do. Because if it gets too complex, then you really do need a sidebar. And so this is where I thought the sidebar would be good. So now let's look at the limit. So the limit, again, as x approaches a of f of x, 2a cubed x minus x to the fourth 1/2 minus, this is not like the geometry problem we did yesterday and we had to apply L'Hopital's rule forever to get an answer. So that wasn't an overly hard problem, but you do get a little bit weary about applying the theorem over and over. That was a fun problem and a good problem to master. Now, when we look at this, and we say, okay, well, you know, if we're in calculus 1, if we're thinking about using continuity, is this expression or this function continuous at x equal a? Well, we have a problem basically here. When x is equal to a, we just get a to the 1 here, so 0 downstairs. And then, of course, that's an issue. But what do we have upstairs? Well, notice here, we're going to get 2a to the fourth minus a to the fourth, which is a to the fourth 1/2, which is what? A squared. And then here, when we add the powers, substituting a here, we get an a squared when we have 6/3. So we get a squared minus a squared, which is 0 downstairs. So the idea is right here, just say upon substitution, since this is a little bit more complicated, I'll write a little more words here. Upon substitution, we get 0/0. So again, the a squared minus the a squared is 0. And of course, the a minus the a is 0. So that's indeterminate. So that's the form, one of the forms that we can apply L'Hopital's rule directly. We don't have to take logarithms or rewrite things algebraically. So now we'll apply L'Hopital because that's the hypothesis that we need. So we're going to take the derivative of the numerator and then the derivative of the denominator. So I guess we'll apply the chain rule here. So we get 1/2 2a cubed x minus x to the fourth to the negative 1/2 And then we multiply by the derivative of the inner function. Again, the x, that'll just live as 2a cubed. And then, of course, here we'll get a negative 4x cubed. Now we differentiate here. Notice that a to the 5/3, it's constant. So we get a minus 1/3 a to the 5/3, and then subtract 1 x to the negative 2/3. Again, that was just a basic application of the power rule. And then downstairs, of course, the derivative of the constant is 0. So we apply the power rule again, and we get negative 3/4 a to the 1/4. And then if we subtract 1, we get a to the negative 1/4. Excuse me, x to the negative 1/4. So when we look at the problem that we have here, and we notice we have one application of L'Hopital's rule, what again we want to do is clean this up a little bit so we can analyze it. All these negative powers are a little bit cumbersome. So let's rewrite it so we've got a much more user-friendly problem. I'm sure L'Hopital students didn't like this problem back in 1696. They probably said, okay, let's start with an easier one. So I'm doing this last for good reason. So now we'll just take this downstairs. So we have 2a cubed minus 4x cubed. And then just take this downstairs. So we have the 2, the 1/2, and then 2a cubed x minus x to the 4th to the 1/2. So that's the first term here, just written in a more user-friendly form. And then minus, so we have a to the 5/3. And then we'll just take the 3 and the x power downstairs. It's like we're doing physics. You know, in physics, you make all your formulas look beautiful. You know, when you take junior and senior level physics, you're just doing stuff like this, and it's a lot of fun. So now here we'll do the same thing here. We'll have a negative 3a to the 1/4. And downstairs we'll have 4x to the 1/4. So this is just a means to make it a little bit simpler. So we applied L'Hopital, and so now we think, okay, can we pass to the limit? Is this expression continuous at x equal a? Well, let's substitute and see. It looks pretty good. Again, because we're not going to get 0 downstairs, so we're in the clear. So now we can say, let's pass to the limit. So let's draw the fraction bar, you know, go ahead and have something to work with. So we have 2a cubed minus 4a cubed, just direct substitution. Again, like I said before, once you look here, there's no problem with division by 0, so you have the continuity. And we don't have any radicals up here that are going to give us any issues, so we're okay. So now we have 2, and then we have 2a to the 4th minus a to the 4th to the 1/2. And then, of course, here we have a to the 5/3, 3a to the 2/3. And then, of course, downstairs, we have a negative 3/4, and then we have an a to the 1/4 divided by a to the 1/4. So that's just going to reduce to negative 3/4. So again, when you're working with fractions, I guess you can check the denominator first and just see that you have continuity, and then you can look in the radicands, and the only issue was here, but we've got that 2 there, so that's not going to cause a problem. So now let's just reduce this. So notice here, we're going to get a negative 2a cubed upstairs, negative 2a a cubed. And of course, we've got a 2 here, which will eventually absorb. And here we have the square root of a to the 4th. So 2a to the 4th minus a to the 4th is a to the 4th. I'll just write this out 1/2. And then, of course, here, notice we have the power rules. So the 2/3 from the 5/3 will be 3/3. So that'll just be negative 1/3, and then an a. Just bring the 3 and write it as a negative 1/3. So we did that one. That's easy. And then, of course, here, the a's to the 1/4 power absorb, and we're left with negative 3/4. So now, if you like, we'll just reciprocate the definition of division by a fraction. And likewise here, the 2's absorb. We have a negative a cubed. And then, of course, the square root of a to the 4th will just be a squared. And then we have 1/3 a. So this is more of an algebra problem, but that's what calculus is. That's all we do is algebra. And so now we have negative 4/3. And of course, this will give us a negative a using the laws of exponents. So negative a minus 1/3 a. And so we've got negative 4/3. And here we have a negative 1 minus a 1/3. So that's again a negative 4/3 a. And so now negative negative will give us the positive. So this will be 16/9 times an a. So again, the computation here is just to highlight the fact that now we're not tied by the theorems just from Calculus 1. That is, those are extremely important theorems, and we've used those theorems here. But getting the ball rolling was certainly much easier using L'Hopital's rule. Otherwise, you're thinking, wow, what kind of algebra would we have to do here? I mean, there are certain instances where the theory takes us beyond the computation. I mean, when you think about it, if you had to apply the limit definition for every single solitary limit you computed, you would run into issues. Now, here's the thing, and this is where I have to, give a plug for theory. In the abstract, we determine limit theorems, and these limit theorems allow us to apply the algebra of limits to a particular function. So for instance, once we clean this up and we say, okay, we have indeterminate form, we can apply L'Hopital's rule. We apply L'Hopital, and then we check for continuity. And then all these theorems about limits ensue, and we do them without thinking about it. It's like the limit of a quotient is the quotient of limits. And so basically what that allows us to do is substitute the value of a and just keep moving until we get a number. So that type of technique is only possible because of the theory of limits. Again, if all we ever had was the application of a definition, for instance, the definition of one-to-one for a function, that would be very difficult. We often need calculus for one-to-one, as we've shown with the inverse trig functions. So there's a nice understanding here, or a nice combination of the new technique with the techniques that you learned in Calculus 1 to do this computation. Now remember, if we don't have one of the forms 0/0 or infinity/infinity, we can always rig it, and that's where the natural log comes in handy, which I talked about last time. So that'll be something that, again, you will use possibly in your physics courses and also in your future math courses and engineering courses. So I thought, like I say, I thought this was a good example to show you that L'Hopital was a good guy. He did attribute the invention of this result to the Bernoulli brother, but it stuck with him, and we call it L'Hopital's rule, and maybe we should say it's Bernoulli's rule, but history is what it is, and it didn't get rewritten. So you know who actually did it, but we are grateful to L'Hopital for getting it out there and making it available in his calculus book. And now in 2020, we're still using results from L'Hopital. So if that doesn't convince you of the profound nature of the calculus, I don't know what will. Okay, so you know, if you keep studying something after many, many years of the discovery or invention, it must be worthwhile. I mean, I think we all realize that every day, and I know you know that. Just taking an opportunity to instill a little bit of humor. Now, again, when you consider the use of the indeterminate form and L'Hopital's rule, we're thinking, are there instances with integrals that may arise that we haven't covered? For instance, with L'Hopital's rule, we're computing limits like we normally think, but we've got a technique that says, okay, try this instead. In integrals, we've been doing to try this instead. For instance, if we couldn't do the integral, we learned integration by parts. If we couldn't do the integral, then we learned, trig integration, or then trig substitution, or partial fractions. So the different techniques for computing integrals is like analogous to the different technique of computing limits of the L'Hopital's rule. So now we want to even move to the next level. That is, what about integrals that we really haven't encountered that have different attributes? For instance, maybe the integrand has an infinite discontinuity in the interval of integration, or one of the limits of integration is infinite. That's something we haven't encountered, and that's what we want to do now. And this is going to be called the improper integrals. And I think you're going to like this. Just like L'Hopital's rule, there will be times when you will be able to use this, and we don't forget anything that we've already learned. With L'Hopital, we use all the limit theorems that we learned in Cal 1. With the improper, we use the limit theorems, and we use everything that we know. We just apply a few different adjustments to move the problem to an actual form that we understand. So that's really all we're doing here. So we're going to call this improper integrals, and we're just going to focus on two types. Later on, you're going to learn more sophisticated types of improper integrals, but this will get you started. So what I have here, we're going to look at two different forms. The first one, for the improper, we will say this: at least one, and I mean, you can get real particular about this, but I thought it would be nice to kind of give you some good examples and roll the theory that way. At least one of the limits of the integration at least one of the limits of integration is infinite. So we replace an A or a B with infinity. Maybe one is negative infinity, maybe one is infinity. At least one would be infinite, and I'll show you how to deal with that. And two, we'll say the integrand, or the function we're integrating, the integrand has an infinite discontinuity. Usually this means a division by zero that causes the function to become unbounded. the integrand has an infinite discontinuity, basically the definition of a vertical asymptote, has an infinite discontinuity on the interval of integration. Now, we're not going to be unkind. We'll just stick to maybe one infinite discontinuity. We're not getting into topological concerns where you have a countable number of discontinuities. That's a later course. So for most of the cases we'll have, maybe the infinite discontinuity will be at an endpoint. And so these will be the types of improper integrals that we will discuss. So what I want to do is give you some examples of these and then see basically how this evolves using what we already know. So let's look at several examples here. Here's the first one, very straightforward and a good example to start with. So we have the integral or the interval of integration 1 to 2. And so what we're going to do, ladies and gentlemen, is we're basically going to compute a limit. And so with the theory of limits, either the limit will exist or we won't, or it won't. So for instance, we will say that the limit or the improper integral converges if and only if limit exists. And then we'll say it diverges, limit does not exist. So you're thinking with an infinite limit of integration, then that imposes a limit. And then if you have an infinite discontinuity, you have to approach from possibly two sides, maybe one side, a right or left limit. Again, that imposes another limit. So when I talk about the limit, I'm talking about the limits that actually evolve from these new types of integrals. So we're going to say converge when the limit exists, and we're going to say diverges when the limit does not exist. So now what we want to do is look at this particular example. Notice here, this integrand has an issue at 1. That is, we have an infinite discontinuity. And what we can usually do is just draw a number line. That is, you can do this in general with an A and a B. But draw a number line and then say, okay, we've got open at 1 and closed at 2. No issues there. And so we would think that we would approach the 1 from the right. This would be a right limit, so to speak. So the definition will be this. And this is where you can choose whatever you like. We usually like A for the lower limit and B for the upper limit. So the issue is at 1. So we're going to say the limit as A approaches 1 from the right. Draw your little number line and get the idea placed into your head, and then say, okay, A to 2. And I'm going to go ahead and write this in a user-friendly way. We'll just say x minus 1 to the negative 3/2 dx. Now, this is where the improper part is basically translated. That is, if you have an infinite discontinuity, you recognize it, and then you allow the variable of integration to approach that particular real number based upon the interval. Now, since this is an endpoint, we can only approach the 1 from the right. And so now when we look at this, we're thinking we have to take the limit of this integral as A approaches 1 from the right. Now, don't look at this and think, well, this is going to require a lot of work here. I don't know what to do. Well, we treat this just like you would normally in a Calculus 1 class. And once you apply the fundamental theorem of calculus to evaluate the integral, then you apply the limit. That's why we need L'Hopital's rule and all these other things to use. So we just drag this along for now, but somewhat ignoring it, just working on this. And then once we have a nice function of a, then we apply the limit, just like we would in a Calculus 1 class. So now we have the limit as a approaches 1 from the right. So notice this is table ready. So we'll just add 1 divided by the new power. So we have the 5 that's already hanging out. The new power is going to be a negative 1/2. So we divide by -2 or multiply by -2. So division by -1/2 is multiplication by -2. We get x minus 1 to the -1/2. And then we evaluate from a to 2. So now you can drag constants outside the limit sign or leave them. It doesn't matter. It's your choice. Usually students like to apply the limit rules, but there'll be times when I'll do it and other times when I won't. It won't make a difference. So we have a -10. And so now we want to apply the 2, replace x with 2. So that'll give us a 2 minus 1. So we have 2 minus 1 to the -1/2. That's just essentially 1 to the -1/2, which is 1. And then we apply the a. So this will be a minus 1 to the -1/2. Now let's translate a little bit more. Limit as a approaches 1 from the right. And if you want, you can go ahead and let me just make room for this. Go ahead and just pull the -10 out. And so, of course, this one's the easy one. That's just 1. And then I'll just write this in a more user-friendly way with the radical downstairs. Now we have a nice function of a, and we can apply the limit. But notice this is fixed, so the limit of the 1 as a approaches 1 from the right is 1. But again, here, what we notice is that this becomes infinite as x approaches 1. This actually diverges to infinity. So we get -10. And we're in this case, we're like, okay, well, that's going to swallow that up. So this is basically -infinity. And this just gives us infinity. So it's just like a negative number times -infinity gives us positive infinity. And so this diverges. So these are the conventions you learned back in Calculus 1, like -infinity times -infinity is positive infinity. That's determinate. Or infinity times infinity is infinity. Or infinity plus infinity is infinity. Those are determinate. Those are, okay, huge and no problem. But when we subtract infinities, that's not determinate. That's not something we can work with. That's a clearly indeterminate. But here, it's like, okay, well, there's nothing we can do about this. And the negative infinity here just engulfs the positive constant. And we're just left with this, clearly not a real number. So we would say that this improper integral diverges because the limit does not exist. Again, everything about this problem is exactly what you would do in Calculus 1. We just simply, for convenience, replaced the limit here with an a to apply the limiting process. Now, there's certain shortcuts that you can use when one of the limits of integration happens to be infinite, which probably is fine. Lots of physicists and engineers do this, but you notice here that all these computations have to do with the properties of the Riemann integral. And then, of course, this is just basically a calculus one limit, infinite limits. And so here you see, okay, as you approach A from the right, or one from the right, this becomes positive, but essentially zero. That defines a vertical asymptote. This becomes infinity, hence negative infinity, negative 10 times negative infinity, infinity. So calculus one is all through this problem. The only new part is just the translation of the improper integral. That is, we translate to a more user-friendly stage. And that way you see that just like maybe a technique of integration, you have one step here. The techniques of integration are probably more convoluted. So the improper part is just getting used to it. Like the first time you use the unit circle, you have to get used to it. Okay, now let's look at another one. Here, what we want to do, and I'm just going to do several examples. I will be honest with you, the most improper integrals that you'll see, especially in differential equations and even in engineering, will be the first type, where actually what happens is one of the limits of integration is infinite. Those are the more popular ones, especially in probability. So let's look at this one. Now, just because these diverge or whatever, don't lose faith. I just want to give you some simple examples at first to make sure you are comfortable with the concept. Because you can look at this and say, you know, it's going to diverge, but let's just first work through the problem. So again, I want to start with some simple problems that are very simple algebraic problems to push the concept forward. Now, notice here, we have the integral from 1 to infinity of the integrand 4 over the quarter root of x, and so, or the fourth root of x. So this integrand is fine. It's nice and continuous on this infinite interval. But like I said before, we have a infinite limit of integration. So that makes this integral improper. So just like we have a translation here, we'll do the same for this. So what we're going to do is, again, usually when you're replacing the lower limit, you use an A, and the upper limit, you use a B, but you can use any letters you like. So what we're going to do, I'm going to use a B since that's customary. I'm going to take the limit as B passes to infinity. And this will be 1 to B. And now we can write this in a user-friendly way. Now, you know, remember we have our tables of integrals, which we can use too when we need. So the idea here is now we're thinking, okay, we have the integral from 1 to B of 4 times x to the negative 1/4, which basically resembles this. So just like we did before, we compute this integral, just kind of leaving this in the background. And then once we have a function of B, as we have here a function of A, we apply the limit and see what the response is, see what the answer is, so to speak. So remember, this is the translation step. Translation step. After the translation, we're back to calculus 1 and any calculus 2 techniques that we have learned. So we get the limit as B approaches infinity. So we have 4. So now, of course, we're going to add 1. The new power will be 3/4, and we want to divide by 3/4. So that'll be multiplication by 4/3. So this will be x to the 3/4. So very simple antiderivatives. We want to start with some basics to ease the concept into the brain here. So now we have the limit as B approaches infinity. And we've got 16 over 3. And then we basically can apply the fundamental theorem of calculus, replace x with B. We have B to the 3/4, and then 1 to the 3/4. I'm doing more steps here than I normally do. Again, just to just to make the process a little bit easier for you. So again, the 16 over 3 can come out. And so now we've got the limit of an increasing function. B to the 3/4 is an increasing function. That's an increasing power function. And of course, 1 is 1. So now we basically just get, as B tends to infinity, this increasing function just gets larger and larger. It becomes infinite, and of course engulfs the -1. So we just basically have 16/3 times infinity, which is infinity. So don't lose hope, since the first two examples don't exist. So we say diverges. So I like to start with these because they're relatively simple, so you can see the technique. So just like a limit, you know, we like our limits to exist, but just like all functions don't have derivatives for every real number, we may not have an antiderivative for a particular integrand. You know, same with limits. I mean, it's all good as long as we utilize good techniques. So again, as I said many times, Calculus 2 is a topics course. We just basically utilize what you learned in the last 2 years and put it together and add some new bells and whistles, and that's pretty much it. Even though I think you realize that you have plenty of work to do, we're basically synthesizing ideas with a few modifications. Now, the one integral that I talked about back in integration by parts, I said we can easily set up a integration formula for this, and I want to go back to that. So when you do, we're going to say something about some Laplace transforms because those will be improper integrals. But I wanted to remind you from the integral table, I think when I derived our formula, I talked about alphas and betas, but I just went to the formula in your book. Let me give you the number. Okay, this particular form is going to be formula 86. So this will be formula 86 from your chapter B. And this is easy to derive just using integration by parts. You're noticing a lot of these integral formulas that we have utilize integration by parts, trig integrals, or trig substitution. So we have this one. So we have coefficients A and B. So A to the U, cosine BU. So we're thinking of the A and the B as the coefficients. Okay, you could use an alpha and a beta if you wanted to, du. And remember when I did that problem, I cleaned it up and made it look nice. And we had something like this. We had the exponential term, A to the U. And then we had the A squared plus B squared downstairs. So we just cleaned it up. And then the terms that after we factored, we have A cosine BU plus B sine BU. And that'll just be the differentiation of the calculus of the cosine function plus a constant. So again, e to the AU divided by A squared plus B squared times A cosine BU plus B sine BU plus a constant. So this is a very useful form, especially when you do differential equations. You know, it's admirable to go ahead and use your integration by parts. You already know how to do it, so you don't have to start over every time you do one of these problems. I wouldn't recommend that because, I mean, this just may be a very small part of a much bigger problem. And then you're going to say, well, shoot, I'm going to use my table of transforms, so I don't have to do this again. So you're going to move up level by level where you take more stuff with you and more ideas with you that you don't have to completely reinvent. So now, if we look at this, maybe we have this improper integral. And so I've given you this formula, which I plan to use in this computation. So say we have the integral from 0 to infinity of e, and then we'll get to use the squeeze theorem, e to the x cosine of 5x dx. So first, when you look at this, you're thinking, okay, well, this integrand is fine on this infinite interval, but it's improper because the upper limit is infinite. Again, you're going to see more of this type in your work in mathematics and STEM. So the first thing we're going to do is just go ahead and translate what it means for the upper limit to be infinite. So we're going to say the limit as b approaches infinity, in this case, of the integral from 0 to b, e to the minus x cosine 5x dx. And now, of course, we can use the fact that we have a nice integral table. We can use integration by parts, but I've taught you about using integral tables, which you certainly have at your disposal now. So I feel free to use them. So now when we compare here, we look at this and we match it up. I'll just go ahead and write this in red. We see that we have an a of -1. So we just match this up. And we have a b here of 5. So when we look at this, this is what's nice about this integral is that we don't have to really worry about anything more table ready. Once we have this, which is this, we go directly to this. We don't have to make any further adjustments here, which is really a luxury, and we like easy. So now let's go ahead and write this down. So this will be the limit as b tends to infinity. In this case, this integral, we're just going to fill this in. This will be, I'll go ahead and use the curly braces. So this will be e, in this case, to the -x. So a, like we have here, now the x is been replaced with x. And then we have a squared plus b squared. That'll be 1 plus 25. And now inside, we'll just go ahead and replicate all of this. So we have a -1, so a negative cosine 5x. And then we have a b, so we have plus 5 sine of 5x. And then we evaluate from 0 to b. So the idea here and what we're seeing with these types of computations is that the use of the integral table is basically, we're saying, okay, now we're going to use the fact that we're more experienced math students, and we now can defer to our integral table, and now we can actually use some limit techniques that maybe we haven't used lately or that we just learned. Let's do a little more focus on this. Now, we want to first apply the fundamental theorem. So the limit as b approaches infinity. So we're going to have e to the -b, replace x with b, over 26 times, and now we're going to have a negative cosine 5b plus 5 sine 5b. Just replace x with b. Then we have minus e to the negative. Now, of course, now we have 0, so I won't put a negative 0, just go ahead and put 0, just negative 0, basically, over 26. And so here we have negative cosine of 0 plus 5 times sine of 0. I'll put the parentheses around the 0 so it doesn't look like an O. So this is where we get to do our L'Hopital's rule kind of thing, because notice that this e to the b can come downstairs, and then we've got this bounded. Well, actually, it's not even L'Hopital's rule. It's just going to be the squeeze theorem. We've got this bounded numerator. So let's rewrite this so it's more user friendly, so we can see the calculus. So if you will, we've got negative cosine 5b plus 5 sine b, or sine 5b, divided by 26 times e to the b. Now, if you think about this, that's really the only issue that we have to deal with. Here, we've just got a bunch of constants. So here we have minus, minus. So this will be plus 1 over 26 times 1. So that's just 1 over 26. How interesting. And then, of course, that's just a 0. Sine of 0 is 0. And then, of course, negative 1 over 26 times 0 is 0. So we're done. Now, this is where we use some calculus, and it's very simple calculus. Notice, and I want you to first observe, we'll do a little sidebar. Observe. The cosine and sine functions are bounded. So the largest, I mean, for instance, when the 5b is like a 4, let's say like a 5, 4n plus 1, odd multiple of pi over 2, this is going to be a 1, so that'll be a 5. So the biggest this can be is a 5. And then, of course, the smallest this can be would be where the sine function would be a negative 1, and we get a negative 5. So what we're saying here, and then, of course, when this is max and min, this is automatically 0. So the thing is that this part right here is bounded because sine and cosine are bounded. So basically what we have in this case is a negative 5 26 e to the b less than or equal to negative cosine 5b plus 5 sine 5b. The sine term is the dominant term, if you want to say that, because of the coefficient of 5. And we just basically see where it would be largest. The largest this can be is 5, and the smallest it can be is negative 5. And of course, that term would be 0. So we have 26 e to the b. And so upstairs, we've got the 5. But that's easy, because now we just see that both of these terms will converge to 0 as b passes to infinity. So we basically have a constant divided by infinity. And so the limit as b tends to infinity, this is kind of the little sidebar you do of negative 5 over 26 e to the b, or I could just do e to the b and be done with this, but I'll write it out. B approaches infinity of 5 over 26 e to the b These are both 0. And so by the squeeze theorem, this must also be 0. So by squeeze theorem, the limit as b tends to infinity of negative cosine 5b plus 5 sine 5b over 26 e to the b would clearly be 0. So the thing is, we're not really applying L'Hopital's rule. We're just basically looking at a situation. And of course, you don't even have to do all of this. If you recognize this, again, you've got bounded divided by something that's becoming infinite. That's like the 1 over x deal as x tends to infinity or negative infinity. We understand the properties of the exponential, and this is indeed an increasing function. So this we get just as a reminder of some of our techniques from Calculus 1, and then as we integrated the natural log and the natural exponential. So as we pass to the limit, this is just 0 as we've shown here, and then we just have the constant, which is not impacted by the passing of b to infinity, and we just get 1 over 26. So the idea here is that there's enough to do in this problem just by considering the limit process. So once you have studied your integration by parts, then you can look at this and say, well, I'm good to go. I've got my nice integral formula. I can pass to the antiderivative here, clean it up with the fundamental theorem of calculus, and then apply the limit. Now, again, this is why we talk about L'Hopital's rule, because there'll be cases with Laplace transform where you're going to need to apply L'Hopital because you may have infinity over infinity. And then one application or two applications of L'Hopital and you're good to go. And many times you can kind of look at that and say, okay, as I start differentiating, this is going to go to 0, etc. So you won't always have to write out everything explicitly. Your understanding of L'Hopital's rule will give you the indications that you need to move the problem forward. So again, we see the marriage of Calculus 1, integration by parts, with the new concept of improper integral. So again, very nice technique where we utilize what we know to get a result that for once, and so what do we say? Converges. I didn't want you to give up on the improper integral. So this was our first one that converges. So again, when we think about the definition, if the limit exists, then we say that the improper integral exists, or we say, just like an infinite series, we say the improper integral converges. Again, converge and diverge aren't really what we use so much with just the basic limits, but I guess we could if we wanted. Now, let's look at an example. Let's see, I don't want to do this one yet. This is coming up. The one thing that's important to remember is that we might have a situation where we diverge by oscillation. So if remember back in Cal 1, and this is to help you out with your WebAssign, if you have like sine x and x is passing to infinity, there is no limit, but it's not because the sine x becomes infinite. You know, it oscillates. So you say diverges by oscillation. So don't forget that. Just remember that limits can fail to exist because they never actually approach a number. They don't necessarily become infinite. So just remember that as you work through these problems. So I want to do an example that will use some more of our calculus. And maybe I'll come back to that other problem I just mentioned. Just want to keep you thinking. And then I'm going to give you the p-integral theorem. So now when we look at an example, again, where one of the limits is infinite, we automatically say, okay, this is going to be an improper interval. And we have 2 divided by the square root. So we're going to get to use some miscellaneous substitution. Our friend, back in Cal 1, when we thought we conquered the world, when we learned miscellaneous. And we see that basically lots of the techniques we've been using have really become miscellaneous substitution, like trig substitution. Talk about changing the integral completely. That's exactly what we do. So here, the first thing we can do is like, okay, well, we know we're going to have to do a substitution. So first we might say, okay, well, do I want to use my shorthand technique? Well, I won't do that yet. But first, I just want to do this. This will be the limit as b tends to infinity, 0 to b, 2 square root x times x plus 3. Now, of course, this is going to be one of our inverse trig integrals when we work with it. So this is going to be a miscellaneous substitution. So with improper, we don't forget anything. We do everything the same way. We just make our translation, and then of course we have extra work to do because of the limit. So don't get impatient with the integration process. Do the integration process like you normally do, and then set yourself up to take the limit. So don't try to put the cart before the horse. If you do, you're going to leave out steps and not really write what you intend. So we'll let the u, we'll do the Professor Ron way. We'll let the u be the square root of x, and then of course we'll square u to get x. So now, of course, 2u du equals dx. Just taking the differential. Again, old hat. We've done this many times. And so now, what will x plus 3 will just be what? U squared plus 3. So x plus 3 is u squared plus 3. Now, again, we're thinking, well, what about the limits? Are we okay? Is everything all right? Well, of course, if we replace square root of x with u as x tends to infinity in this particular case, so does u. And so when we switch to the u variable, this is not going to change. And then, of course, if x is 0, u is 0, so the lower limit's not going to change. Again, we have 0 as the lower limit, and of course we have infinity as the upper limit, so we don't have to worry about making any changes here. Maybe I could have held off on this before we did this, but this is still true. Now we can do this with confidence, so we'll just say new limits will still be b and 0. That is, b will pass to infinity and 0 is just 0. So we have limit as b passes to infinity, 0 to b. And now we have 2, and then we have dx is 2u du. And then, of course, square root of x is u. And then, of course, x plus 3 is u squared plus 3. So, going to be a lot easier than we thought. So we have the limit as b approaches infinity of the integral 0 to b. And of course, the u's absorb, and we're left with just a 4 du over u squared plus 3. So now when you look at this, ladies and gentlemen, you're thinking, okay, this is the first day when we had Calculus 2 with Professor Ron, when everybody was happy. Now nobody's happy anymore because it's hard work. And and you think I'm too tough on you, but no, I'm not. I want you to reach greatness. So remember that the next time you're cursing Professor Ron, that I want the best for you, but I want you to earn your grade. So now when you look at this, you're thinking this is just inverse tangent. So we can do the 1 over a, and then the inverse tangent of u over a. So this will be the limit as b approaches infinity. So we have the 4, which just hangs out because it's part of the integral. So we have 4 square root 3. Again, notice a squared is 3. So that gives us a is the square root of 3 that we have here. Then we have inverse tangent. This is a whole lot easier than the last one. And this is a form that we remember because it's so simple. So then we have u over the square root of 3, evaluated from 0 to b. But now we know that the inverse tangent is bounded, so that makes this computation easy. You know, we did learn something in pre-cal, right? So we've got what, 4 over root 3. And so now we have the limit as b tends to infinity. Let's apply the fundamental theorem of calculus. So we replace u with b, so we get inverse tangent of b over the square root of 3. Sometimes physicists just put infinity there for b. That's the shorthand I was talking about, which I'm fine with. It would not matter if you did that, but for now, maybe just do it the standard way. And then, of course, we have inverse tangent of 0. So the idea is that we remember from our work with the inverse tangent that it's bounded between the horizontal lines negative pi over 2 and pi over 2. So of course, as b tends to infinity, this term approaches pi over 2. And of course, inverse tangent of 0 is 0. So again, just remember, let me just write this down. We know this. Observe that the inverse tangent here is bounded. So the inverse tangent is bounded between these two real numbers. And so as b passes to infinity, the inverse tangent will approach pi over 2. So this is very straightforward application of our knowledge of inverse tangent. So we get pi over 2. And then, of course, inverse tangent of 0 is 0. So this gives us 4 pi over 2 root 3. So this will give us 2 pi over root 3. So not all of the problems have to be long-winded and difficult. We see now that you know, once you basically know some integration techniques, you can really talk about improper integrals. Again, if calculus 1 just lasted forever, you know, we just say take calculus. The course lasts 3 semesters, and we don't call it Cal 1, Cal 2, and Cal 3. We just call it calculus. Well, you can do an improper integral once you know the fundamental theorem of calculus, which means that you know that the integration and differentiation are inverses, and how to calculate a definite integral. Once you know that, you can do improper. Maybe you can't do a whole lot of examples, but I think the working knowledge with improper integrals is allow students to be able to compute enough types of integrals so that this has more meaning. And so that's why Calculus 2 has become the topics course. It's kind of like the catch-all. You get everything you need that you need to use in future classes, and then Cal 3 is just Cal 1 in 2 and 3 dimensions. So the idea is that now we're seeing that the techniques here really just rely on what we already know, not by what we've learned so far. We just learned one translation procedure, and then everything else is exactly what we've already been doing. So I think you're going to find the L'Hopital and the improper integrals and the integral tables to be tools that you put in the tool chest to make your life easier, really. And of course, allow you to do some really interesting problems. And as you become engineers and do modeling and all, you will often think about improper integrals because you will have variables that will pass to infinity. Now, what I want to do is just give you a fairly straightforward result that has to do with the computation of a p integral. We're going to have a p series, but this is just a standard result that I want you to know, and it's easy to prove. We'll just call this the p integral theorem. We'll have a p series that'll look just like this, pretty much. P integral theorem. You can spend a lot of time classifying certain types of improper integrals, but if you know the definitions that I've given you, how to translate, then you don't have to memorize a lot of things. You know the technique. And so here's what's going to be the case. That is, if we integrate from 1 to infinity, the integrand, in this case, 1 over x to the p. So you can look at this and see kind of what's going on. When you look at this integral, it actually does converge when p is greater than 1. So we're going to say it actually converges to a real number that we can write down. It's not the same for the series, though. P minus 1, 1 over p minus 1, when p is greater than 1. And then diverges, basically diverges, becomes infinite when p is less than or equal to 1. So you're thinking, okay, well, we kind of get 2 for the price of 1. Now you're thinking, well, we could have, maybe we can make some allusions or back to some earlier problems and say, okay, well, we can apply this. The interesting thing about this result is that now not only does it give us a nice variety of integrals that we now know, it automatically gives us the actual limit, which again is a gift, kind of like the geometric series, which we take for granted. So when you look at this, you're thinking, well, how would we show this? Well, it would be easy to show, and I want you to use this. So this particular result can be applied however you like. And notice that there's flexibility here with the lower limit. You know, as long as we're making sure that this is defined, there's flexibility with the lower limit. Now, why is this true? Well, most of the cases can be done in one step, but the one case that requires separate analysis would be when p is equal to 1. So when p is equal to 1, what is the key here? We just get the integral from 1 to infinity of 1 over x dx. And you know what this is going to be. This is just the natural log. So you're thinking, oh, this is not going to converge. So you're going to say, okay, well, this is the limit as b approaches infinity of 1 to b of 1 over x dx. But this just equals the limit as b approaches infinity of the natural log of the absolute value of b, which again we'll be able to get rid of, 1 to b. So this will give us the limit as b approaches infinity of, now of course we can retire the absolute value here, natural log of b minus natural log of 1. I'll go ahead and just put these in parentheses for clarity. And now you just see, again, the natural log is an increasing function. This becomes infinite. It takes its time, but this swallows up, well, swallows up the 0. Nothing to swallow. So here, this becomes infinity. So for 1, we know it diverges. So for all the other cases, we can just assume P is not equal to 1 and just get a general result. So here for P not equal to 1, we'll just get a limit which we can analyze fairly simply. So again, we'll start with this. We'll have the integral from 1 to infinity. And now what we'll do, we'll just write this as x to the negative p. So just write 1 over x to the p as x to the negative p, just for ease in computation of the antiderivative. So this will be the limit as b approaches infinity of 1 to b of x to the negative p dx. So now we get the limit as b approaches infinity. Again, just remember, you've got a nice recipe here for the integral. So add 1 divided by the new power. So this will be x to the 1 minus p divided by 1 minus p. So then add 1 divided by the new power. So add 1 to minus p, we get 1 minus p divided by the new power. 1 to b. So this will give us the limit. So this will make it easy. We can retire both of these cases here. So this will be, if you like, 1 divided by 1 minus p. And so we replace x with b. So we get b to the 1 minus p. And then replace, again, replace x with b. Now replace x with 1. So we get minus 1 to the 1 minus p. So in that case, 1 to any power again gives us 1. So that's easy. So if you like, we can write this as limit b approaches infinity of 1 over 1 minus p. And then just write this downstairs. So this will be 1 over b to the p minus 1, minus 1. Now, one more step. Again, you want to make this easy to see. 1 over 1 minus p. One over b, p minus 1. Now, if you look at this, and this is just like what we've done before, as b passes to infinity, in this case, b is bigger than 1. So we'll think here that b is clearly larger than 1. That's what we say, much larger than 1. Then this is a number that's between 0 and 1. And so, of course, this will converge to 0 as long as p is bigger than 1, because you raise a number between 0 and 1 to larger and larger positive integers, then that particular expression will converge to 1. But now, if p is less than 1, then this power becomes negative and this reciprocates. And upon reciprocation, you're just getting a number bigger than 1 raised to larger and larger powers. So now this says, what does this equal? Well, we're going to get 1 over 1 minus p times 0 minus 1, which is, again, this will flip everything around, 1 over p minus 1, when p is bigger than 1, and then diverges, or infinity, when P is less than 1. So that completes the proof. So the idea here is we're thinking about what happens. This is why you write it this way. You think of raising numbers between 0 and 1 to larger and larger integer powers. That converges to 0. You prove that in calculus 1. But then if you raise numbers bigger than 1 to larger and larger powers, which happens when P is less than 1, then that clearly diverges to infinity. That's just like a power function. Then they're increasing. So the idea here is that we can look at the case when P equals 1 as a separate case, because of course it wouldn't make any sense here. We can't have P equal 1 here. It doesn't make any sense with the integral. So this analysis part must be done separately. But for all the other values of P, they can be taken care of here. And so now you've got a very nice result here. You can replace P here with any number bigger than 1, and you know what the answer is. And so boom. So this is a very, very useful result, and something that can be utilized to save you lots of time. So what I want to say here is that this is very useful. Now, of course, if you're doing a problem and you're asked to say converge or diverge, then you can use this result. Don't say, oh, well, I've got to do all of this again. No. Once we do the result, you know it. And of course, if we're in a face-to-face class, I might have you prove this on the test. So you get a freebie. You don't have to prove this on the test. But again, if we were face-to-face, I'd probably say, okay, I want you to know this proof. So how is this gonna help you in your virtual class, in your distance learning class? Know this, put this on a note card, know this result and use it. And that's almost as difficult as knowing the proof, because then you have to feel good enough about the result that you remember to use it. One thing that we often remember is that our brains don't always work very well with what our goals are, because we have to be confident in our knowledge in order to use it, because it's not going to be on the tip of the brain if it's not in the secure category, so to speak. Okay, so the P integral is something that we want to use and use often. So again, we're going to have a P series, so don't forget about that. Now, what I want to do are some more examples. I keep coming back to this. I'm going to do this problem. I keep bringing it up. I think that's just like my brain telling me, don't forget this problem, Professor Ron. They need to see it. I put that together after I was thinking about some other problems that I wanted to work on, and I got it here ready to go, and I keep putting it in front, so that shows you I want to cover it for you, or eventually cover it. Now, the next problem has to do with an application that we did back in chapter 7. And basically what this says is compute area bounded by the curve and the x-axis. So compute area bounded by the curve and the x-axis. So we use a lot of that calculus. Remember, if you're rusty on some of those limit theorems, go back to your Cal 1 notes and go through those proofs, because those are important. They're not hard proofs, but they use the epsilons and the deltas. Now, here's the function. Y equals 12 over x squared plus 9. And you're thinking, well, you know, that's back to the arctangent deal. Well, the thing is that this is a nice even function. And if you just thought about a picture of it, you know it looks like a curve, a bell curve. Again, you don't have to have a picture so much, but you know, we've got 12 over 9 right here. So we have something like this. We have a nice symmetric curve. So in this problem, you're thinking, well, that's improper because this, when we look at this function, not only we see y is even, and also that we see y equals 0 is a horizontal asymptote. That's just pre-cal. And so this is necessarily improper because we want the area bounded by this curve and the x-axis, and the curve is infinite. We're not chopping it off, so to speak. So now we're thinking, okay, well, we can use the fact that we have even function to retire one of the limits of integration that will be infinite. So for instance, here we'll say area formally would be the integral from, well, of course, now, I mean, you know, take x, let me not just mow over this, to be a real number. So we'll just start positive. So there's our rectangle. And we know that the width is delta x, and the length here will just be y equals the function. So the upper curve is the 12 over x squared minus 9, and the lower curve is y equals 0. So to get the area, we have to integrate from negative infinity to infinity the y dx. So we have 12 x squared plus 9 dx. But now there's nothing wrong with looking at this in terms of the symmetry of the curve, which is to do the following. We'll just say we'll do twice. This is like the Cauchy mean value principle. We'll just say 0 to infinity, 12 x squared plus 9 dx. I mean, even though we've got improper integrals, we certainly have symmetry. The area over here would be duplicated over here or replicated. So the idea is that let's just use some symmetry. And now we can say, well, this will be 2 times the limit as b approaches infinity. Now we're back to the integrals we've been doing. 0 to b, 12 x squared plus 9 dx. So you get some practice using the inverse tangent, which comes up a lot in probability. That'll be something you all will see again when you take your probability courses. So now we're good to go. So this will be 2 limit as b approaches infinity. So again, we have the arc tangent. So this will be 12. Okay, a squared in this case is what? 9. So we get 12 over 3 inverse tangent of x over 3 evaluated between 0 and b. So now we get a 4 here. So that'll be a 4 times a 2. So this is 8 limit b approaches infinity of inverse tangent, replace x with b over 3. Again, we know it's bounded above by pi over 2. So again, the same computation. So now, just like we had before, the inverse tangent of 0 is 0. And of course, as b passes to infinity, this is just bounded above by pi over 2. So this is 8 times pi over 2 minus 0. And of course, the 2 into the 8 is 4. So you just get 4 pi. So this is a very simple calculation. Again, not at all difficult, utilizing our knowledge of the inverse tangent so you can find areas even if the actual region is infinite. And you get some real interesting anomalies here with volumes of solids of revolution and areas and all. You'll get some things that don't seem to be right, where you've got where you've got a finite volume, but you've got an infinite surface area, or vice versa. These problems can be very perplexing. The mathematics and the real world often find each other at odds. But again, it's just the way the mathematics is set. And even though the mathematics describes our real world, what we might think is the case is not always mathematically correct. So not always can we rely on intuition. Now, here's an example that I want to talk about before I get to that one that I can't seem to forget about, which is, and there's several examples here. This one is called the transform, the Laplace transform. And this is, again, an improper integral where the upper limit is infinite. And I just wanted to mention this. For instance, suppose this finds its way into complex variables, differential equations. It's all over the place. Suppose f of t is Riemann integrable. Riemann integrable, in this case for t positive. And what we're going to do is let, in this case, f of s be the improper integral 0 to infinity of e to the negative st. So s is going to be a parameter. So this will be a function of s, f of t dt. And of course, for s element of R, a parameter. So if the improper integral exists, if the improper integral exists, then we write f of s equals, and this is the L is for Laplace transform, L of f of t. The Laplace transform, and Laplace was a French mathematician, the Laplace transform of f of t. Of course, there's also a Fourier transform too. The transform methods are useful because they help to smooth out functions and make them more user-friendly. You transform functions in differential equations, make it into something you understand, and then you do the inverse transform to get back to the original functions. It can be an arduous process depending on the complication of the problem, but it's a very elegant result, just like the Fourier transform that you will see in your future classes. So the idea is basically when we compute the limit here, there will most likely be restrictions on s, just like we had restrictions on p for the p integral. That is, for certain values of p, the p integral existed. We'll have the same here. We'll have like s will provide hopefully some values for which this improper integral exists. And so you're thinking, oh, I see, this is like an integral table. You could have a table of Laplace transforms. And so what we do in calculus is we look to find transforms for types of functions that come up often, like polynomials, trig functions, I mean, things that we use readily in calculus. So let's do an example here. And I've got one that I made up. The one in the WebAssign was easy. It was too easy. So I've ramped it up a little bit. Maybe I'll put this one on the test. So for instance, here's an example, and we'll work this with the Oliver Heaviside approach. So for this, what we want to compute L of f of t in this case, where f of t is actually just the function t, like a polynomial. So this is where we get to use maybe some of our L'Hopital. And I thought this would be a nice way for you to see that there is use of the L'Hopital's rule, not just an academic pursuit. So here we're thinking, all right, now we're going to have an integral, and we're going to have e to the minus st times t. So by definition, so you can Google this and look at tables of Laplace transforms. By definition, L of t will be the improper integral 0 to infinity e to the minus st times t. Now, of course, this is like the problem that we did with the exponential times the cosine function, which, you know, that was good to know. But this integral is not as hard. It doesn't repeat. The t just differentiates to 0. So we can do this one by hand just for some practice. So now first, what does this mean? This means the limit, in this case, as b passes to infinity, of 0 to b e to the negative st times t dt. So all we need to do is get an integrand or an antiderivative here, and we'll be done. So let's go ahead and do this the easy way. So this will be good practice. We'll do d and I. So now we've got t, which differentiates to 0, and of course e to the minus st is easy. So now what we're going to do is we're just going to configure, at least at this point, that s is fixed. So you do this as s is fixed, and then you get an answer. And when you pass to the limit, you'll be able to determine for which s's the limit exists. So now we want to think of s as a constant. So we get t differentiates to 1 and then to 0. And then we get, this is like the kx like deal. So negative 1 over s e to the negative st. And then we do it again. So we get another copy of negative 1 over s. So negative times negative is 1 over s squared e to the negative st. So again, the idea here is that this procedure is fairly readily done and not too difficult to replicate. So we get plus and a minus. So now we have the limit as b passes to infinity. And so now we can fill all of this in. So notice we have a minus s, 1 over s, and we have a t and an e to the minus st. So let's write this in a user-friendly way so we can think L'Hopital. So let's do the minus 1 over s first. One over s. And then we're going to put the t upstairs and the e to the negative st downstairs. So write it like that. So we can think of applying L'Hopital. And then here we have minus, again, another minus. So minus 1 over s squared. And then, of course, we'll just take this downstairs so we can easily see what the limit is. Okay? So sometimes, like when we're doing our analysis, we retire negative powers so we can kind of see how things may become arbitrarily large and give us an easier way of identifying convergence or divergence. And so then, of course, we have what? 0 to b. So now we have the limit as b passes to infinity. So now we'll replace the, in this case, the t with the b. So minus 1 over s times b e to the SB minus 1 over S squared e to the SB. And now we've got minus, so now we've got minus, notice here, minus all of this, so these just become pluses. So might as well go ahead and write that in, minus, minus, pluses in all cases. So we put in the 0, we get 1 over S, 0 over e to the 0. Of course, that term's going to be 0. And then we get plus 1 over S squared times 1 over e to the 0. And that's non-zero. So now this is where we can think of the L'Hopital. Notice here, this one's fixed. This is just a constant divided by e to the SB as b passes to infinity. As long as S is positive, this will become infinitely large. So now we're thinking, all right, we've got a restriction right there. So this is going to have S positive. So moving forward, we've got to have this restriction for that limit to exist. And then likewise here, we'll apply L'Hopital because again, as b passes to infinity, this becomes infinite. And as b passes to infinity here, this becomes infinite. So let's apply L'Hopital. So we have limit as b passes to infinity. So we have negative 1 over S. And then the derivative of b with respect to b is 1. And then, of course, we have S e to the SB. And then, of course, this limit's 0 by just not L'Hopital, just by the fact that this becomes infinite and that's constant or bounded. So we have minus 0. So I'll just say minus S squared times 0. That's the first part. And then over here, this is just all fixed. That's 0 plus 0. And then, of course, that's just 1 over S squared. And now we can, again, let's see what the limit is. Now we're back to this part. Now we have a fixed number divided by e to the SB. And as b passes to infinity, this becomes infinite. So now the limit, this is 0 now, based upon the fact that that one was 0. So we get the same thing. So we get minus 1 over S in the limit times 0 plus 1 over S squared. And so our response is 1 over S squared when S is positive. So what we're saying, we treat the S like a constant when we apply the transform calculus, but then we say, okay, if we want these limits to exist, just like with the p integral, we can specify here, as long as S is positive, this limit's 0. This is going to require L'Hopital because this is going to give us, this is infinity over infinity. So we apply L'Hopital and get 1 over something that blows up, which clearly goes to 0. And then this is just fixed. So now we see the Laplace transform of t is 1 over S squared. So this is an interesting construct where you're thinking, this is insane. Why would I ever do something like this? The idea, ladies and gentlemen, is that the transform process, just like we take the rational expressions of sine and cosine and convert them into a rational expression in u or x or whatever, that we can apply an integral formula or partial fraction decomposition. This is the same thing. This makes the actual functions simpler. That is, we can now solve a differential equation because we have a simpler construct. And then once we get a solution, we move everything, we inverse the transform. We invert the transform and move everything back to the original functions. So that's the purpose of a transform method. And Oliver Heaviside, he did all of this. He did the shortcut methods, the engineering mathematics. I mean, he was a guru in mathematics, and that's why we still use his techniques. So in your WebAssign, you actually get to do the Laplace transform of 3, which again, not a very complicated problem, doesn't even require integration by parts. So I thought I would throw this one in just as an extra. And then of course, if you're interested and you have extra time, you should Google the Laplace transform and look at a partial table of them and maybe try your hand at practicing this and get a step up on your differential equations class. There's plenty of stuff. Last time I taught Honors DE, we completed the entire chapter on the Laplace transform in the Zeal DE book because the students liked it so much. I said, we could stop. I said, but let's just go ahead and finish it if you like. And they were all for it because they really enjoyed it. But it got kind of tedious towards the end, but it's a useful transform. Now, the problem that I keep thinking would be interesting, again, is infinite discontinuity. Now, there's a problem where you actually try to figure out when an actual improper integral exists, and you're going to use properties of logarithms. So don't forget the properties of logarithm. Now, what I wanted to do was just give you an example of a improper integral, which is really an arc length. But the way it's stated, ladies and gentlemen, you don't really need calculus because it's simple geometry. But the actual computation is useful. So what I'm going to do is a arc length calculation. That is, for instance, this is an example of an arc length calculation. I'm not even going to tell you what the original function was. You'll be able to figure it out. But when you read the WebAssign problem, you're going to say, I don't need calculus for this. I know what the circumference of a circle is. And I looked at this and I thought, well, you know, my students are not going to do additional work when they don't have to. I wouldn't expect you to. But the process of actually doing the integral is good practice. So let's just say that we were doing an arc length calculation. And this is what we had to do. So this is good practice. But I kind of chuckled when I thought I assigned this problem and I thought, well, they don't need to do this. But then I said, I'll get something good out of it. So for instance, we're obviously talking about a circle. So if you did an actual arc length calculation, you would actually get this integral here. Now, when you look at this integral, even though I know we've done more with the infinite limit of integration because those just occur more often in science and mathematics. They're all over the place. You can't get away from them. But when you look at this particular example, lots of times students will ignore it completely and luckily get the right answer. But when you look at this particular integrand, we see that it has an infinite discontinuity at 0, just like the first problem that we did. And so when you think about this, just to get some practice with this, you think, okay, well, you've got your 0 here, and you've got your 7 here. And so you're approaching 0 from the right. So this is an infinite discontinuity. Infinite discontinuity. Continuity at 0. My goodness, if you can just spell the continuity and differentiability and integrability, I mean, if you can just speak the words, your friends will think you're very brilliant. The terminology in mathematics is not simple, but it's how we speak. Most people like to say derive it when they mean differentiate, but I'll let that pass. So the idea here is that we're thinking, okay, we're going to approach 0 from the right so we can introduce a variable a. So this will be the limit as a approaches 0 from the right of the integral. Let's write this more user-friendly. So we have a to 7, and then we have 7, then we have, well, and you know what? We don't even need to do user-friendly because we already see a form. We already see the form of this. So forget that. You know what this is. So we've got 49 minus x squared. So we don't need that. It'd be a waste of time. So when you look at this, you're thinking, okay, well, this is our friend, the inverse sine form. So at this point, you're like, okay, well, I'll integrate this and then I'll apply the limit. So we have the limit as a approaches 0 from the right. And now we've got the 7, and this is a squared is equal to 49. So we get inverse sine of x over 7. Remember, the 1 over a is non-existent for the inverse sine form, a to 7. So this is our, remember, our inverse sine form. Inverse sine integral form. And so now we have the limit. We can bring the 7 out if you like. Limit as a approaches 0 from the right. Apply the fundamental theorem. So this will be inverse sine of 7 over 7 minus inverse sine of a over 7. So then we get 7 limit as a approaches 0 from the right. And so now, of course, the 7 over 7 is 1. So we have inverse sine of 1, which is our friend, minus inverse sine of a over 7. So now when we look at this, all right, I didn't write that 7 very well. I tried to repair it and it didn't work very well. So let's just do that. There we go. So now we can pass to the limit. This is fixed. So we have 7. This will be pi over 2. And then, of course, as using continuity, a will pass to 0 from the right. So this will be in the limit inverse sine of 0 over 7. So this will be 7 times pi over 2. Again, we use the continuity of the inverse sine function to move the limiting process inside. And this, of course, is sine of 0, which is 0, inverse sine of 0, which is 0. So that gives us 7 pi over 2. So the key here is that the way that the calculation was stated, you would not need to use this approach because you know the circumference of a circle. That was what I thought was interesting about this. So I think I may make a suggestion, but again, the idea is if you actually compute this just as a separate integral, not as an arc length, but even I wanted to let you know where I actually found this. You can ignore the improper nature of some integrals and luckily get to an answer that's correct. That will sometimes happen. And I tell students, I said, be very careful. If you're doing a computation, you want to make sure that your work is good. So what I tried to do here was just morph this in just to an improper integral problem and just say, okay, here's a nice example of where we have an infinite discontinuity. So again, we don't always have to use major integral techniques. We can do the more straightforward ones that we know, like the easier integration by parts, and then of course the more complicated ones we can use the integral table. And I wanted to show you an example that utilizes an integral table in closing. And I'll just summarize it. It's the last problem that we have in the WebAssign. And this is a good example. The top problem is just the Laplace transform we did. So let me just move this up here. So this is kind of an interesting example, ladies and gentlemen, and I wanted to share it with you just to kind of summarize it so you can work through this on your own. Now, the problem says, for what value of C does the integral converge? And then I'm thinking, okay, this is a nice trig sub, but you know, we're like, okay, we don't have to worry about, you know, doing everything from scratch. I mean, there's value in practicing your integration, and there's also value in utilizing the integral table. So when you look at this problem, this is kind of like the P integral. This is like we're doing a Laplace transform and we're trying to figure out, you know, that's a strange question. So I've got to figure out which C will work. Well, here's the thing. The first integral is just a substitution, a trig substitution. So what I did is I went to the handy integral formula and just wrote down the integral form that matches this one. This is formula 31. So we can just go from here using this formula directly. And then of course the dx over x plus 1, that's just the natural log. That's just du over u. That's really simple. So now what we see here is that the u is equal to x and the a squared is just 1. So we can exercise the definition of improper integral. That is, we'll have b passing to infinity of 0 to b of 1 over x squared plus 1 minus c over x plus 1. And this is what I was talking about, properties of logarithms. So now we'll use this integral form to get this answer. Again, we have the logarithm of x plus the square root of x squared plus 1. Now, hopefully this is getting very simple. If it's not, then you haven't been paying attention to me, because this is easy. This is where you get to ride the wave using your integral table. And then of course we just get c times the natural log of the absolute value of x plus 1. Now, just like I said before, apply the fundamental theorem. So we replace x with b to get b plus the square root of b squared plus 1 is the argument of the logarithm. And then for the b here, we just replace x with b. We have this. Now, of course, when x is equal to 0, we just have 0 plus the square root of 1, which gives us 1, and then we just have 1 there. So both of these terms are going to go away, you know, which is fine. The fewer terms, the easier. So these are both 0. And so now you can use, this is what I was talking about, using the properties of the logarithm. We're going to use the power rule to move this up, and then the quotient rule to collapse the difference of two logarithms to write this as the log of a quotient. Now this is where we use our pre-calculus and our calculus 1 techniques. Notice here, as b, this is what we're going to use when we talk about sequences. As b tends to infinity, this really behaves like a b, you know, the square root of b squared. So that's really a power of 1 upstairs. So if this is going to have any hope of converging, the power of b will have to be the same in both numerator and denominator. So this is what Webasine was asking you to do. So the only way, since the top is approaching 2b, the only way the limit's going to occur is when c is equal to 1. So that's the analysis that we've been doing in the class today. And so now when c is equal to 1, we just have the limit as b passes to infinity of this expression. And so now as b passes to infinity using the continuity of the log, we just get b plus b upstairs, and then of course b downstairs, and 2b over b reduces to 2. So what's interesting about the improper integrals is that the added adjustment of writing the limit means that now you have to transport yourself back to calculus 1 and then also possibly use L'Hopital's theorem to compute the limits. So this is actually going to make you a better math student. So what you see here is you have a very interesting problem which requires you to think about properties that you discussed in pre-cal and calculus 1. So indeed, if c is equal to the natural log of 2, this integral converges. So we did it in a backwards type motion. So what I want to impress upon you is that as you're working your tests, you have full freedom to use an integral table, because I've taught you the integral table. There may be cases where you're going to say, okay, well, I can't find this form in the integral table. I'll just use the partial fractions or whatever. I'll have some of those. But there is nothing that says you cannot use your integral table that I have discussed in the class. And this is an excellent example of that. And when you get to your physics classes, your university physics and electricity and magnetism, when you get to your junior level and senior level engineering and physics classes, as my former students are now going through at Texas A&M and U of H and even some at UT, they're like, Professor Ron, it's all the calculus. That's all you're going to do. So you're going to get an opportunity to use all of this, and it's going to make your understanding even that much better. Of course, this is great conversation for family reunions if you want to clear the room. If you just want to start talking about math, everybody's going to find something else to do. Unfortunately, as I was growing up, no one ever wanted to talk about math, but since my musical side, they always wanted me to do music, so that worked out okay. But math will clear the room. If your intention is to get everybody cleared out, just bring up improper integrals and maybe that'll work. So what we're done now is that we have completed the work with the chapter 8 with the conclusion of the improper integrals. So after this, what we're going to do, ladies and gentlemen, I think you're going to enjoy this. We're going to move into sequences and infinite series. And so we're going to use all of the techniques that we've already set up, and then plus review some basic concepts about sequences and series, and move into the integral test, the geometric series test, monotone convergence theorem, comparison test, ratio test, things like that. This will be the beginning of analysis when it comes to adding up infinite sums. And even though that sounds like a contradiction in terms, you're going to really become better math students doing the infinite series. It's kind of like the integration techniques take you to the next level. So that'll be the next thing that we do. So rest up, get your homework done, get your quiz done, and then we will, again, if I don't see you at my conference hours, we'll start back up with chapter 9 on Monday and get busy with the sequences and the series. I appreciate your attendance today. I hope that you're enjoying the material. It's challenging, but it's really very rewarding. And maybe you've decided that becoming a STEM professional has been an excellent decision. So I wish you well as you study. Everybody have a good day.
Thank you, Professor Ron.
Thanks. You all have a good day. I appreciate that.